Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about how we can apply Newton-Raphson's method on nonlinear systems of equations. So the last time we did this in our scientific computing series is we talked about different methods that we could use in order to find solutions, to find roots. But we did this based on linear systems. So based on line equations. And we talked about three different methods of doing this. One was the bisection method, where we start with 2 points and we say they have different signs. And if our real value function f is continuous, then there must be a root between those two values or those 2 points. And so we get their midpoint or the center. And then we look at the sign again. And if, let's say, this x sub c, that point, and x sub l, so the other point, let's say they have different signs, then the root will then lie in between x sub l and x sub c, right? So if they have different signs, then that's where the root lies. Else, if x sub c and x sub r are the ones that have different signs, then the root lies in that interval. And we keep doing that again and again until we find the root, could either be exact or approximate, and we call this the bisection method. And we even talked about the Newton-Raphson method, where we start with an initial guess x naught, and so we linearize or we make the function f a line. So this is our line where we have this initial point of the function f of x naught, and then we take the derivative of that function. And so this is kind of like a line thing, right? Because this is the slope. This is actually in point slope form, believe it or not. And we find the root by making it equal to 0. We keep going and we see that, oh, we get this thing, right? So to get to that point, we get the initial point minus function of that initial point divided by its derivative at that initial point. And we use an iteration scheme to do this. So I think this was a Jacobian iteration scheme where sub j is our current point, x sub j plus 1 is the next point. And we keep going and we make sure that the derivative shouldn't be 0 or else this would be undefined. And we call this the Newton-Raphson method. And if we don't know our derivative, then we approximate the previous iteration, and that will give us the secant method. And so those are the three methods we went over. Okay, so let's talk again about Newton-Raphson method for systems of equations. And so let's start by writing the linearization around x sub j, right? So our linearization or our line is at the function x sub j, so our current point, plus its derivative. And we multiply that by some x value minus that current x sub j. And then from there, we use its root as the new guess for the root of f, right? So here we say, okay, we say that our function f is continuous, and it's a set of all real valued. We're going to say our function f is a vector. So it's a multi-dimensional function, right? So we actually call this a vector function or a multi-dimensional function. And we're saying this. So f of our x vector, and so we put everything in that function, f sub 1, f sub 2, all the way to n, right? And we're saying that x is actually just a vector. F x sub 1 all the way to x sub n, right? And so the linearization of f around f, okay, let me just write it. So the linearization around of f around our vector at j is given by this. So we say L, and now we get that vector. This is equal to our f of that. So that's the first iteration. And then here we use a Jacobi. Right? And then this is just going to be this. So now here we're taking into account vectors. And so we say that f is, or f consists of a vector that has equations in it, line equations in it. And then we plug in that x vector in there. And so we solve all of those one by one, and we get a resulting vector out of it. That's why we use this Jacobi thing, right? And so we say, what is actually this Jacobi thing? Well, Jacobi is when we plug in our f function there, this will actually just give us partial derivatives. So with respect to x1, it's actually a matrix. Oh yeah, this is f sub 1, f sub 1. This all the way to n. Then we keep going. So this is f sub 2. This is x sub 1. This is going all the way to f sub n 1, f sub 2, x sub 2. And we basically just keep going here. This goes to n. This goes to n, n, right? 2 all the way to, and I just complete this part. N, right? And so we say that this is a Jacobian. That's what it means. And so if we want to characterize this thing, well, the Jacobian is just an element of all real numbers, n by n, right? And so actually finding the root of this linearization of L of x is done. So we can do this. Through, we set it to 0, because that's how we find the root of something. We set it to 0. We get its Jacobian, f of x at that current point. And then, okay, here we're just plugging in what we do know. And this is equal to negative, right? How do we know it's negative? We basically just use this one. So minus f of this, right? That's how we were able to derive that thing. So here, this is equal to negative of this. This is basically equal to 0. And then from there, let's isolate. Now this is equal to, so here this is just some algebra. This is all the way to the power of -1. Then f are negative. No, I already have the negative here. So this is, there we go. Right, this is to the -1. I could put this as the denominator, doesn't matter. And then from there, now we have our solution. So our next x is basically just this thing. Right? It's that thing. And then that will give us the iterative scheme. So here we say this is the next point, j plus 1. And then this is our j. So here now we use a Jacobi iteration scheme. Right? So this is our next one, j plus 1. And so that's basically that's the algorithm of the Newton-Raphson method. Now, here's the thing. How could we translate a linear system to a multidimensional root finding problem? Right? So let me just write out. So how do we translate a linear system to a root finding dimensional problem, multidimensional problem? Oops. How do we do that? And so we want to solve basically a system of linear equations here. So here we're not even getting into the nonlinear yet. So basically the idea is we want to solve something like this, right? This is all the way to n, or yeah, n. And this is b. Let me continue. 2, 1, x 1, 2, 2, x 2, 2, 3, x 3. Right, and then we basically keep on doing that until we reach n. n2 x2, n3 x3, n x n. Oh, that's n. So it's an n by n matrix. The n. Right? So we want to solve something like that. We want to find their roots. So when we do a root finding, Well, we basically want when root finding. So we want our A of this thing, our AX equals B, to be AX minus B equal to 0. And then that's how we find our roots. So we basically just have to set that whole system equal to 0. And we want to see them as functions, right? So what do I mean by that? So here we have f sub 1, x1. So here we're plugging in our x vector, x1, x2, all the way to xn. And here that's basically our thing, right? So that's the first one here, x1 all the way to here, minus b. So 1, 1, 1, 2, all the way to n minus b1. Or bn, actually. Yeah, bn. Oops. Wait, is this n1? Okay. Apparently it says in the notes it's bn. Anyway, so something like that. We want to see them as functions. And so if we do j here, well, we do it again, all the way to xn. This is just replacing every index of the row by j. j2, x2, jn, xn minus bj, right? And so from here, we basically see that our f, when we plug in this vector as our input, is just, yeah, basically this. Our matrix A times vector x minus b vector, we basically think of them as a function. And so our Jacobian, when we think of this, is actually just equal to A matrix. Right? That's just equal to our A matrix if we get their Jacobian. Not sure how exactly, but there has to be some derivation there. And so from there, we now have that the scheme becomes, so here's the scheme. The scheme becomes like this. So we have x j plus 1. This is equal to j plus, or I'm kidding, minus this Jacobian. This is f of x j, negative 1, and then our function at that point. Right? And then this is just equal to our x j minus, and here we said that our Jacobian is equal to our matrix, so it's actually our matrix inverse. So there was a reason why we weren't putting it in the denominator. It's because we want to treat it like an inverse. So that's our inverse in linear algebra. And this is, again, our f of xj. That's just, again, we treat it like a function. So like this. And then I think if we simplify it even further, let me see. If we multiply its inverse by itself, by its own matrix, is this? So the thing is, I haven't done linear algebra before. Okay. Because I don't want to assume that the inverse is equal to, or when I multiply the inverse by its original, it's the identity matrix. I don't want to assume that immediately. But apparently the simplification here, why is it the simplification? Wait, let me actually try deriving it myself. I just want to complete it, like the whole thing. This is its inverse times itself minus its inverse times this. And then, then what happens here to these terms? We can factor out this xj thing. So this gives me 1 minus this. Right? Okay. There has to be something that's canceling here. And I'm just trying something. Or I could factor out the identity and see what happens. Or just leave it as is here. Wait, let me leave it as is here. Yeah, I don't want to get into the computation of things because this is a scientific computing course. But basically, that's how the end of it is going to look like. It's just its inverse times the b vector. And so here we can see that it's no use to use Newton-Raphson in this case. However, for a nonlinear system of equations, it is very useful. Oh, so in this case, this one's very useful for nonlinear. So that one I didn't know. So when we say nonlinear, we mean equations that are not aligned. That's it. So x squared plus y squared equals 1, y equals x squared, cosine squared equals sine squared over cosecant. I don't know, something like that. But basically, they're not lines. So not like y equals mx plus b. Okay, let me see. Let's do an example of a nonlinear system. So here we have cosine x sub 1 plus e to the x sub 2. That's sub 2, right? Okay. Plus x sub 3. This is equal to 3. So immediately we can tell this is definitely not your typical line equation because we have trigonometric functions. This is tangent, and here we multiply both x1, x sub 1 and 2. Then here it's a natural log of x3. This is equal to 4. And then lastly, we have x1, x sub 1 plus x sub what? Oh, x sub 1 plus x sub 1 plus x sub 1 is negative 3. So that's a nonlinear system. And so what do? We treat them as functions, right? So when we treat them as functions, we have f1, f2, f3, right? And I'm just going to copy paste. Because that was the first thing we want to do. We treat them as functions. Oh, shoot. That's not symmetric. That's not good. Okay. Oh, this is nice. There we go. Accurate. So we treat them as functions. And then we do a Jacobian of our function. Am I going to write the whole vector thing? I don't need to. Because this is an example. So this is sine of this. So here what we're doing is, again, from a previous lecture, the idea is we're trying to make these systems or convert these systems into its matrix form. So this is cosine Oh, wait, my bad. Why is this cosine squared? What the? That's interesting. Wait. Let me see what's happening. Oh, so we take its derivative. That's what we're doing. Cool. Okay. Cosine squared. And then this one's yes. So the derivative of tangent. What in the world is the derivative of the tangent? I think it was secant, right? So when we're getting the Jacobian of a function that consists of vector functions, we're taking the derivative of each of them. And the Jacobian is basically a matrix. Okay, so it's secant squared, or in other words, it's cosine squared. Now, there is a reason why we do it cosine squared, and that reason is apparently it doesn't work if it's secant for some reason. I did try doing secants in my computer programs, and it doesn't work for some reason. Don't know why. It's buggy. And then, okay, 1 over x sub 3. And then this is 1. Right? If we take the derivative of, oh, my 1 was left here, of this, then that's that. Right? And actually, the thing is, we're doing partial derivatives here. We're actually doing partial derivatives, right? If we remember here, we're taking partial derivatives. So that's that. And then from there, well, what do we do now? Oops, no, I can't see. And we can actually use this to approximate the solution to this problem, right? So approximate solution to problem, right? Now we can use this. Okay, let me show you all a quick code of how exactly this is going to work. Let me. So that's basically how it's going to work. I'm going to quickly share this screen. So here I'm going to do it in MATLAB, right? So this is our function, right? Function f, and it's Jacobian. We get Jacobian. So here, we can zoom in. Here we have the function, right? And then we have our Jacobian of that function right here. And then from there, we get a number of iterations here. And then for our index, we do a for loop. Here we're doing our scheme, our iteration scheme, and then we end. And then here's another thing that we could have done, right? And I think this one is doing a while loop this time. And we're trying to find when it's greater than this. And then this one's secant rule, which doesn't work most of the time. So if we remember our secant rule when we reviewed, here we're approximating. And then, yeah. Anyways, I'm going to run all of them. And I want to see. That's fine. I'm going to run all of them. Oh, I should have just done xj here. Let me do xj. Let me display it. Okay, actually what I'm going to do, here's what I'm going to do. clear this. Okay, let me go ahead and run this part. So here we see our xj is this. And apparently it's that's our xj. It's getting closer and closer to a particular solution, right? It's this one. What does that I mean? I think that means imaginary or something, meaning it doesn't converge to some value. Wait, let me just double check what that means. Oh, they are, yeah, they're complex numbers. So meaning they're not real numbers, they don't exist. Okay, cool. And then here we look at this one. So now I'm gonna run this part. And I'm gonna display my xj as well as my counter. I'm gonna run this part. So here, I don't know if you guys can see, this was the previous thing. Here it's pretty much the same thing, but then the number of iterations it went through is 10. So we did this for 10 times. In order to get to a norm where it's greater than its tolerance, 1 to the e negative 13. And then here's a secant rule that we also did. And it doesn't work most of the time. Then we have their Jacobians here. What's this? Okay, here I'm gonna just display this counter and then this xj. I'm gonna run this particular section, and here, does it run? Oh, there we go. It ran also for 10 times. Here's the approximate solution. So yeah. Okay, next time, probably in the next videos, I'm gonna make more in-depth discussion on these types of things. But for now, yeah, this is a brief overview of what approximating solutions or roots are for nonlinear systems and even linear systems. They work for both. And yeah, I hope you guys enjoyed, and I'll see you all in the next one.